Okay, hi everyone. Thank you all for being here. Thank you for the amazing talks of the two other people that came before me. I'm a PhD student at McGill, and I also work at the Quebec Institute, and I'm also a research scientist with, oh, he disappeared. Because where we work on like putting any African-based like research into production. So today I'm going to be more like looking at an overview of everything that I've done, that the Masakane community have done, and some perspectives and everything. So I will start by the lack of integration, because this is something that everyone has talked about. But we can look at whatever currently exists. Like for instance, how do I? Yeah. If we look at, let's first of all look at this, If we first of all look at this, I guess, graph, let me just call it graph here, we can see that African language accounts for more than 31% of all living languages in the world. But then when we compare it, for instance, to every voice assistant that exists, we have 0 of them. Like, I bet none of you has like Swahili, for instance, embedded in his Siri or something like that. Now, if we move to text-based, which is a little bit easier, then we have like Google Translate that is stopping the effort by relatively 20 or 30 languages. DeepL is not integrating any, and then Yonder's Translate has mostly like 1 or 2. The second aspect is the fact that we also have lack of LLMs, which are now the cornerstone of almost everything that we do in NLP and in other applications. Like yesterday, you've seen how they can be used in drug discovery, for instance, in healthcare. So I've fetched those data, for instance, from Hugging Face that I assume that everybody uses here. And if we look at this is the percentage of multilingual pre-trained language model with African languages. Not even exclusively African languages, but with. And it's a very small ratio of everything that is. It's only 1%. I mean, that has even been rounded. On the other side, I've shared a few of like the most up-to-date use African multilingual pre-trained language models, AfrexLMR, AfriBeta, and the one that I work on, AfroLM. But then it's supposed like up to 23 languages, which is still far from like the almost 2,000 plus that we have on the continent. And this goes also back, for instance, to the lack of like data sets that we had of resources, and affect also those like information from Hugging Face data sets. And we can see that from everything that exists, only 2.1% have a focus on like African languages, with, of course, African languages. So it's not even data sets that are entirely for African languages. And then coming back to what Vikosi was saying about representation and everything, if we compare the overall CI publications that exist and that are over the internet, less than 1% are about African languages. So from here, how can we move forward? Because I presented the challenges. Now, we've been doing some effort to actually start working on those, because we can't always be complaining that there's no data, there's no this and that. So here are some efforts that has been led by many amazing folks, most of them from the Masakane community. This, for instance, has been the first machine translation data set that I co-created with my colleague and friend Chris, for the first and still up to date, the unique machine translation from Fon to French and French to Fon, Fon being my native language spoken in Benin. Now, we have many other data sets, like for instance, the Masakaner, for different purposes. And recently, we've worked on AfriSpeech, which is, at this state, the largest Pan-African speech corpus for clinical and general usage, incorporating 120 African accents. And also the cross-lingual question data set for 9 African languages that was presented at NLP 2023. Now, we have now data sets, how now we move forward. One thing that is important to know is that we have Okay, so there are two situations. The situation where you have a language that is not covered, but that does not mean that there's no data. And the other situation where there's like truly no data. So you have a situation where you don't know what exists, and you have a situation where there's nothing that exists. But then in the situation where you don't know what exists, you still fall in the trap of, okay, what can I build? Because you still don't know which data to use to be able to build any type of system. That's why we worked together with Chris. This is his idea. I remember it was back in when we were studying in Russia in our student rooms. After the FFR project that we worked on together, because we faced a huge problem building and gathering data sets, and then we were like, okay, so what about the other 7,000, or no, 2,000 African languages? And then we've worked on Lanfrica. This is also his credit. He spent most of the time on it, and we've tried to make it a very open source. So if, for instance, you are looking for a data set, like, I don't know, in AFL, something that you won't find on the internet, you easily can go on Lanfrica and find it just like in a matter of like seconds. You can even try it now. The other thing is that there are people who are linguists, who are like annotators that actually have that as a profession. But I don't know if you, I think I said that yesterday, but it might be more relevant here. Like a part of the data that have been used, for instance, to train ChatGPT in like RLHF style so that we have the system that we have today, has been created by Kenyan workers. But then they've been paid less than $1 per day. But you can see how big and huge profit OpenAI is making from it, right? So from those people, for instance, we've been trying, we are still working on it. We've been trying to make it in such in a way that they could actually also profit from the work, and then like maybe have some type of benefit from it. So that being said, I'll move on to like what we have actually started implementing, because we moved from the challenges, the fact that there were lack of data representation and everything, and then we created some. Then how do we move forward to start building those systems? So the first thing that we've built, for instance, this was also Chris and I at NLP 2021, was the first multilingual machine translation for 6 African languages. It covers like Igbo, Fon, you can see it on the screen. So here we use mainly the MT5 based models, and with the many-to-many translation like task. We leverage 2 different approaches, like for instance, fine-tuning with back translation, and back BT and rec. What rec technically means like reconstruction. So technically you corrupt your inputs and you want to force your model to learn to recover those inputs. It might be more relevant in context of, I don't know, like self-supervised learning, where you are trying to learn a robust representation, for instance. So here we have a few key insights. For instance, if we focus like on, let's say, for instance, Fon, those like look at the position where Fon is at the end. Fon has not been used in the original pre-trained corpora of MT5, which was like MC4. So if you look at it, you will see that Fon benefit more from back translation. And if you look at Igbo, which was actually included in the pre-training, in the MC4 dataset that was used to pre-train MT5, you will see that Igbo benefit more from the reconstruction. So that's where we join many of like other words that conclude that yes, back translation is definitely better, but then it's even better, for instance, if you want to increase the performance of your model on the downstream language, you might have higher chances of achieving higher performances by including it in the pre-training set. And then we compare it against the Flores 100 benchmark data set. Flores has been used to train M2M100s, and like the 200 version has been used to train the NLP machine translation model. And then we got like gains ranging from like 0.8 from Swahili to French, and like up to 1946 from French to like other languages. Now, the next thing is about the same stage of effort. So what I presented was about machine translation, but then we have many other works, for instance, like the Masakana one, we have Masakana POS, and many others. And one thing that is important here, for instance, that was, I think it was at NLP 2022, where we look at how we can, this was specifically for name entity recognition. We look at how we can efficiently transfer learnings from like huge pre-trained language models to like our specific languages, like how we can adapt them. And one thing that we saw was there were quite a few key components that were important. So for instance, one of them was a geographic distance. So if, for instance, you are training a model, you want to improve the performance of your models, for instance, on, I don't know, let me say Zulu, you might benefit more from a language like Xhosa, which is geographically closer. If you want to do, for instance, Fon, you might benefit more from like a language like Ewe, which is like spoken in Togo. And there are many other attributes, and we have very great insight on that paper. Now, the next thing is about, because we talked about data is what we repeat all the time, but then how much data do we need actually to perform something relatively well? Relatively, because well is a relative notion. Like what is good for me is not necessarily good for you. So here we developed, and you will understand a little bit why we have the title, a few thousand translations can go a long way. So here we developed like the first and biggest African news data set for machine translation, and we leverage different like learning approaches. So for instance, continual pre-training, many-to-many translations. We transfer several like, different domains, like the news one, the religious one. Religious one now is a little bit restricted because of like license issues, but is huge. Like you can imagine as a corpus, like GW300 with like gigs or like maybe terabytes of data. Religious news has just been like crowdsourced and like manually translated. So there were human linguists and annotators that took part in the tedious task. And we did it with a grant, I think, from like Lacuna Fund as well. So yeah. So one thing that is, the commercial. Okay, cool. So one thing that, the first thing that we tried to see was whether we can benefit from fine-tuning or directly from zero-shot performance. Sorry for the technical details in like the translation, but then what we can see here is, for instance, like M2M100, when we perform in zero shot, first of all, it doesn't have as many as language as we needed, and then when we look at the performance on Wolof is fairly low, very. Now, look at the same performance after we fine-tune it. It is still not that good, but you can see that there's a huge jump between the zero shot one and the fine-tuning one. And same thing, this is like according to the blue metric, and this is like the character F metric. Now, this is for the direction of English or French to African language. If we look at the other way, we can observe the same thing. Like, obviously, the translation, how am I going to say, performance is lower because our language have more complexity, but we observe the same trend. After fine-tuning, we have a boost. So the conclusion from this experience was that, yes, fine-tuning helps. Now, how does fine-tuning help? We try to see if, like, we try to perform some, like, domain analysis, domain shift analysis. As I was telling you, we had, like, religious domain and we had, like, news domain. Now, religious domain was, like, huge, thousands of gigs, for instance, or a few terabytes, and, like, the news was very small. So what we can see here is like we have a strong bias. If you train, for instance, your model on news, on religious, and you want to evaluate it on news, the blue score is very low. It's extremely low. It won't perform well. But then if you pre-train, if you like fine-tune on religious, on like the target domain that you're interested in, so here, for instance, the news domain, you can see that it brings way more and better performance. Like, have the blue score that we use. So what we had as conclusion is that if we have some models that are trained on like religious data, they are not capable of translating news well because of like a huge and strong domain bias. And that's literally what I say. So if we have this, what do we actually need? Like, how do we adapt? Like, how do we use that like insight, and how much data do we need to perform like in a target domain well? So after performing some domain shift adaptation analysis and like adaptation, we found out that we can actually perform way better when we do that on the target domain. That is the main thing. The main key here is that if you have a data set, you have a task in a specific domain, you will benefit more from fine-tuning on the target domain than fine-tuning on any other domain. It will give you more boost. Now, here goes the good question. How many data we need? So we look at like English to Swahili, English to Igbo, and like French to Bambara, and we train a bilingual transformer as our baseline. So for each of them, we wanted to see how much data we need to outperform our baseline, which is this like red dotted line. And in each of those cases, more or less, we can see that, for instance, for English to Swahili, we need 2.5K. Same here for English to Igbo, and like 1.5 or something like that for French to Bambara. That means that we don't need, and like there was a very beautiful report from like Sebastian Rieder yesterday that was also showcasing that like from at least 1K human translation, you can actually boost significantly the performance of your MT models. So this is actually where the conclusion we had is like, we don't need huge data, we just need good data, even if it's small, and it is in the target domain, it can significantly help you to improve your predictions. This is where the title comes from. A few thousand translations can go a long way because of the finding that we had in the paper. Now, another interesting thing that I'm probably mostly focusing on like my PhD is like we have, let's say, no pre-training models on the language. How do we cope with data scarcity and like ensure that our model is robust and everything? So this is where I talked about like active learning, a fairly interesting concept that I discovered when I was working on a drug discovery research paper, actually. And then I was like, okay, can I actually leverage that and try that in the language where the data set was also like very scarce? And turns out that it works. So basically the data set that we used, like our data sets, was like missing a lot of other existing data sets. And this is like the statistic per language. We covered 23 languages, but like all of them are not here. Now, basically, I'll try to summarize it very shortly. It's like in active learning, what we want to do is like a semi-supervised learning way. What we want to do is like we have a model. We want to teach a model to learn to pick samples that are going to be more useful for him. So for instance, if I'm a computer science teacher here and then I'm looking for students who are like good in like C++, I don't need to like go through all the students that are in the class. I have been somehow trained to maybe look at a student, learn some attribute, and from there pick exactly which student I know that might be good to be able to help me like to ease the task of me teaching C++. So that's technically what is it. So we have, for instance, we initially start with some like labeled data. We have the model that we learn. Then we query on a labeled data set that is also called pool. And then we add it to the initial data set, and then we start the whole loop. It hasn't been extensively used like in NLP, but the few ones that are survey papers that leverage it have shown that we can achieve like very high accuracy with as little as 20% of labeled data sets. Like using 20% of like a data set that you have could be enough to achieve a very high accuracy. In another ways, like this allows you to discover, if you have a big set, it allows you to discover a small subset of the big set that has as enough information as the big set. So you don't need to just be learning everything. You know exactly what you focus on to like improve your performance. So, sorry for the figure, but that is technically what we had in the paper. The graphism was not that good. But yeah, so we have like N languages. We build our data set randomly, so this accounts for like 80%, this accounts for 20%. Each time they are like randomly sampled, and then we use it to train the model, to train the language model. And then from the prompt data set, the header data set we build, we get some prompt by masking 15% of like the language of like the sentence. And we use our model that we train to generate more sentences. And then those sentences are added to the new batch that are then added to this initial set, and then like retrain the whole system. Now here is important that we get sentences that are not as close as whatever was here, otherwise we're going to have like redundant sentences. So for that we impose some constraint, like if we want, for instance, like an example could be, for instance, we have two sentences, like the original one and the generated one. We can compute something as simple as, like, for instance, a word error rate, and then we don't want the word error rate to be like 0 because otherwise it will be that it matches exactly the original sentence, but we don't want it to be entirely 1 either because it will mean like it's completely garbage. So we try also like to manage that. So we did some experiments on name entity recognition, NER. Sorry. We need some experience on like name entity recognition, text classification, and because the model was trained on like news domain, we performed some sentiment analysis that are a type of like, in this context, out of distribution experiment. So what we found out is that our model, first of all, like the active learning here, because if you compare these two numbers and these, they are significantly different. Now, if we compare, for instance, to AfriBeta, our model outperforms. If we compare to MBERT, that has been trained on like trillions of data sets, our model also performs better. And we also observe the same thing for XLMR base. So we have our entire data set after the whole training that we did was about like 0.73 gigs. And it still outperformed like every other model that was pre-trained on that vast like maybe 14 or like 1,000 times bigger data set than it. Now, what we try to do here is like the NER experiments on additional language, because for the Massacana data set we had 2 versions. So in the second one we had 11 additional ones, and then we used that as well. And what we can see is that our approach also works not significantly, but works better than the 2 other approaches. So that tells you, oh, this is test classification. Anyway, so here in the test classification aspects, what we did was like to use AfriBeta and like to perform basically like a classification. So obviously like the margin was like very small, but overall we had a better performance than AfriBeta large. So now when we come to the out of distribution setting, we can see that our model performs significantly better than like AfriBeta, for instance. All of those shows that our active learning approach is significant and that we are sampling and generating like very useful sentences that are now after helping. So overall, like the conclusion is that we can actually use active learning and build models that are very data efficient, that achieve like state of the art, like against like models that are pre-trained on like huge and vast amounts of data, and it also generalizes well. Now, this has all been about text. How can we adapt it to speech? Because most of our African languages have like atonal, and not all of them have like low like text available. And it goes back to the presentation of Mr. Mark, who was saying about like the data annotation, like the annotation of the labeling. So here we adapted the same thing like we did for AfroLM, but then we induced a few other ideas. So here the task is like we have a pre-trained language, like ASR model, not language model, ASR models that we want to expand to a new set of diverse language or an accent. So what we have as challenge is that we have very limited labeled data. Actually, we use the AfriSpeech data set, but the context is we want to see, okay, how much small we can start and how much of data we can use but to actually be able to achieve better performance. So we constrain ourselves to the situation where we have very small limitation, like we started with 30% of initial data set. And all of those accents and language in the data set have highly complex in morphologically, and most of them has no unlabeled data, for instance. That's the scenario we put ourselves in. So we want then to be able to use the small data that we put apart to create a model that is maximizing on the whatever rate downstream tasks on each language and on each domain. We want to reduce the cost of annotation while ensuring high quality labeling and increase the robustness and generalization. So here I've already explained what active learning is. Now, one key other component is uncertainty measures. So technically, episteme comes from, I think, epistemology, which is referred to knowledge. So epistemic uncertainty is how uncertain the model is due to the lack of data. But then there are interesting ways of incorporating those informations back in the model to improve the performance. And one thing that is interesting is that they've been, this was on the efficient network. So here on the left, we have, for instance, the neural network that predicts that we have a typewriter keyboard with 83% of certainty. And here that we have a stone wall. But we all can see that it's none of these. But then you can look at the certainty. So it is better to say, okay, I don't know much about this, than to say, okay, I know about it, and to be wrong. So it's better to not be confident in the wrong, if I can say so. So this is what we wanted to avoid. And technically, as humans and as the way we try to teach machines, we cannot separate it from uncertainty. Even the aspect of learning something new embeds already the uncertainty aspect. So I'll skip, maybe move forward. That's a very, very basic definition of uncertainty using the model variance, the variance of the model prediction. And this is what maybe we want to minimize. We want to minimize that variance to make sure that our model is as robust and reliable as well. And there are many ways of doing this. One of the approaches that we've used was to use mutual information that I talked about yesterday in my talk for the medical aspect. And one of interesting in the active learning setup, we use mainly what we have, we call acquisition function, what allows us to look at the unlabeled pool of data that we have and know which sample to select. You have to select your new sample, new data point according to certain criteria. So here, one of them, for instance, BARD, which is fairly good, tries to maximize the mutual information between the model predictions and the model parameters. So it's operating in the space of the model parameters. So there are many ways of estimating epistemic uncertainty. Two of them are MC dropout, where you technically just turn on the dropout layer of your model, and then you have it to, if you run n times the model on the input, then you have n different result. And then there's a deep ensemble, which is far more expensive. So here we use the Waterer rate. We here have something we call U-ware as our selection criteria, and we use MC dropout. And the sampling mode, we have what we selected was the most uncertain one, and we have several different baselines. So this is the free speech data set. You can scan the QR code. I'm not going to go through the slide. And then those are the different statistics about the data set that we've used. So this is the system that we had. It's fairly the initial AFRLM, where we started with 30%, and we look at these as held out data set, our pool. So here we have some interesting results. If we try different models Wave2Vec, Hubert, Nemo, those type of things, and after we compared it against Whisper. One thing is, for instance, Whisper is not able to perform MC dropout because Whisper medium or base are not built in with the dropout component, but large is very expensive to work with. So the main key, for instance, from here is that if we look at the performance, Waterer rates over the baseline where we use 100% of the data set, and over our approach where we use, for instance, after everything we use up to 60%, so we use like up to 40% less data. In some domain, in some accent, we use way less. We can see that our models significantly outperform all of them in all domains, across all domains, like the general one, the clinical one, both. Both is when we merge together the data from the general and the clinical domain. And then we tried it on other data sets to make sure that it's also data set agnostic, and we can see that the performance, the gap is huge. So if you take the ratio, for instance, of the best performance and, for instance, of the baseline, you might end up with 69% of whatever rate reduction, and across different like models, you can see how huge the model, our approach has improved the performance on the downstream task. So here we did some very basic analysis to see how well our metric that we define is helping the model to adapt to those new accents. What we can see, for instance, on the clinical, let me first of all go quickly to the general domain. We can see here, for instance, on the general domain that we have the top 10 uncertain accents. Here is the first adaptation round, the second one, the third one. As we are acquiring more and more samples, you can see that the distribution of whatever rate across those languages achieve like a perfect one. We can also see the same here for like clinical, but it might be more challenging. So there might be some other threshold about, okay, how much data do I need to like query at once? And then when we use it here together, we also have more or less the same trend with some like level of like discontinuity. So overall, like we found that using this, we can use very small data and like very generalized, build generalizable ASR model to the context of like accented African clinical ASR, and that we can instead, like when we learn from most informative data sample, we make it very suitable for low resource settings. And this has already been trained, like for instance, tested like in hospitals in Nigeria and all those type of things. So I'm gonna fast forward. Another thing, the last thing I'm going to talk about is like fun. And here we use like the multitask, which is about, okay, I want to use a single model to do several things. So fun is like a very low resource language. It has almost none, and very few NLP applications except the one that I built with my collaborators. So the task is the same thing, but here we want to maximize the downstream performance on several tasks at the same time. So how do we do that? On multitask learning, we have different approaches. For instance, this is like the way that we share the parameters across the task, and this is the different, I can say paradigms, the hard parameter sharing, and then the like soft parameter sharing. In this work, we combine something together. So here, instead of what we do is like we have two different LLMs that we use to get representations, and then we merge those representations in a specific way, and then after have different linear models that are then producing specific losses for each task, and then we backprop through the entire models. And here we have like fine-tune over all languages, and then we have fine-tune entirely over like font. So what we found out is that if we fine-tune, for instance here, these are the other pre-trained language models that we have. We see that if we fine-tune only, for instance, on font, this is like when we fine-tune only, when we fine-tune on all, and this is when we fine-tune only. So if we do this experiment only on all languages and then evaluate on font, we have better performance than when we do entirely and solely on font. And this is the same, we got the same like trend across the POS and across the NER baseline. So that means that we can leverage some like cross-linguality and benefit from it like while doing those type of experiment. And this goes back to what I was saying about one of the papers where we've shown that you can use languages that are geographically close and benefit from it. And here we just leverage, like I told you that we try different merging, representation merging approaches. And here we just leverage two of them, like the multiplicative one and like the additive one. And funny enough, the multiplicative approach looks better. And This is the intuition that we came with, but then obviously we haven't been able to prove it yet, so it's just an intuition. So technically, this work was definitely about this is the first effort to use MTL for NLP downstream tasks in phone, and then the result that we've done have shown very competitive performances compared to single models' performances. If you look at all of this, and yeah, so as future works, we want to answer the question, which other language in the data will benefit the X language that we are considering, and then explore dynamic and average losses. So I'm going to quickly rush because that's the end of my presentation. I'm still young, as everyone. I just have 26 years old. So I hope that this presentation carries a little bit of the whole background and everything that has been done. And then what I would like to picture is that we need to focus on creating more resources for African languages. Now, we need to engage more in community effort, as Vikosi has been saying, and then we need to lead more Afrocentric research, because when I go to conferences, well, the number has been increasing, but if you go to iClear, AMLD, you have barely a few black folks. It's not good. We need to be more representative. Now, we need also to build techniques that are more adapted to our language. For instance, I use the active learning example to show that we can barely use a very small and limited amount of data, but then still build something that is very robust and efficient. And this is also my African dreams. That's what I already talked about, that we need more and more people I won't say like me, because there are many others, but we need more research scholars, people who actually want to understand the deep core, how those models work, and come with ideas. Why not the next big thing, the next transformer type of model comes from Africa? It would be good. And as we are working toward all of this, it's also good that we integrate them into products, so that, for instance, one day I can use my phone and speak Siri with, I don't know, my mom of my kids, or teach them, and you can also do the same. And it goes also to many other works, for instance, to be able to type all those things, we need more keyboard and autocomplete systems. So I think that's going to be all. I took more time than I think I've been given to, but I hope it was insightful.
Thank you, Bonaventure. Thank you very much. And I also want to thank you for being so eagerly active on the WOVA platform. I want to say to our public that you have been already answering questions online, and that you will be kindly continue doing so throughout the conference. So thank you. We will be taking one question from the audience before moving up to the next presentation.
Thank you very much. My name is Dr. Mugoe. I wanted to ask, how does the model that you've just presented compare to AfriBeta after we perform what we call dimensionality reduction on the data set? Can we achieve the same using dimensionality reduction and then use something like AfriBet and achieve the same result? So how will it compare? One, how does that compare to that? And two, how is the difference? Thank you.
Okay, so interesting question. We haven't leveraged that to perform those things you might want to go to, some things PCAs or those type of things. We haven't. So I can't, out of the blue, tell you how much it works, unfortunately. But you can try and then let us know the result.
Thank you very much for being honest. Because the principle in the model you've just shown, which is a very good model, I like it, is based on dimensionality reduction from the data set. And
not really.
Yes.
Not really. So if you look at dimension, if we want to look dimensions, you can, for instance, if you have a speech input, the dimension is technically the number of features that you extracted, right? So we are not performing it here. What we are doing instead is if I have 1,000 samples, I don't want to look at all the 1,000 samples. Maybe I just need If I have 10,000 samples, I don't want to look at all 10,000 samples. What I want to look at is at maybe 1,000 or maybe 2,000. Maybe those are already representative enough, or the entire 10,000, to give me the information that I need. So the idea is like we want to start as small as possible and maximize the performance on the downstream task in the least amount of adaptation. And after, we also perform like some active learning performance experiments where we don't look at the labels of like the data set that we put aside. We instead use the model, the ASR model, to generate transcript. Now, obviously, if you are doing ASR, you need like some like input and then some targets, which are the transcripts. How do we then like know which transcript is better for the input? So then like we perform like some little bit of like some hard maps across the different generated input, because here we use MC dropout. So if we have an input, a speech that we run n times, we are going to have different representations, and all of them are going to lead to different transcriptions. So then we take, for instance, maybe ideally high-level idea, we take the representation and the word error rate, the transcript, and we compute maybe like the distance between them, and then we compare the word error rate of each transcript. So if I run the model n times, like 10 times, like we take each transcription as target. So like the first transcription becomes your target, and you compare it to all the other 9s. The second becomes the target, you compare it to the other 9s. And then at the end of that process, you find the thing that is like, that has the lowest word error rate, and that builds you like the better representation. And that's what now you use as like synthetic generated, and then now you put it back. This is, for instance, in the active learning setup. So it's not really about like the dimension that we are reducing. It's more about like how much minimal we need to max out the performance.
Okay, thank you. I think we shall further that discussion after the session. Okay. Thank you.
Thank you.
Fantastic. Thank you, Bonaventure. Our next presenter is an accomplished AI researcher and data scientist. He is currently making significant strides in AI throughout his role as co-founder in Intelliverse AI. And today, he will be explaining us how AI and virtual reality can help revolutionize cultural heritage in Africa. Ladies and gentlemen, please welcome Cornelius Moroa. I want to take this time for a gentle reminder. We have our partner platform, WOVA, and this platform allows us to exchange, create topics, and meet up. So please feel free to use it as you wish.